Hi, my name is Isa, and today I want to talk to you about nuclear fission and fusion, two processes that can release enormous amounts of energy and can thus be harnessed to power our cities and our world. Before I get into what these two terms mean, it's important to talk about something called binding energy. The binding energy of a reaction is the energy required or released when that reaction takes place.
Let's look at this graph of binding energy per nucleon versus mass number, where as we go along the x-axis, elements become heavier.
The process of fusion is to fuse or join two lighter nuclei to form one heavier nucleus with a greater binding energy, while fission is the splitting of a heavy nucleus into two or more lighter nuclei with greater binding energy. So how can we figure out how much energy will be released by a fusion or fission reaction? This can be calculated using the mass defect, which is the mass difference between the reactants and the products of a reaction. But what about conservation of mass? This is explained by the mass-energy relationship, E equals mc squared, which shows that we can equate the mass defect of the reaction with its binding energy. Let's look at an example where deuterium and tritium fuse into helium-4 and release a neutron, which actually takes place in our Sun. Using the masses of each of the reactants and products to obtain the mass defect, we can figure out the binding energy. The mass defect in atomic mass units can be converted to kilograms and then plugged into the mass energy equation to give a binding energy of 17.4 mega-electron-volts. So, why does this matter to us? Well, nuclear fission is a process through which we currently obtain our nuclear energy. But it has a problem, nuclear waste. The radioactive nature of the waste and the amounts generated make it dangerous and difficult to store. Enter nuclear fusion. One bathtub of water and one lithium battery could theoretically provide the energy needs of a UK citizen for 7 years. So why do we use fission and not fusion? Fusion requires extremely high temperatures, like 100 million Kelvin to occur, and currently we're not able to make a fusion reactor output more energy than is put into it. So fusion ignition or a self-sustaining reaction doesn't happen, which means that fusion is not commercially viable. Thankfully, research from places such as ITER in France or the Coulomb Centre in the UK, which houses the Joint European Torus, or the JET, give us hope that we will soon be able to achieve fusion ignition and produce significantly less waste than nuclear fission reactors. That's all for today. Thank you so much for watching.